Hello students, welcome back. Previously, we went through the problems associated to the increasing-decreasing nature of the original function, which is not presented, versus the graph of the derivative function. So, do not look at the increasing-decreasing nature of the given function, because that's not what this problem is all about. This problem is asking you about the increasing-decreasing nature of the original function, not this function. So if you answer increasing decreasing of this very function, then you get automatic 0 credit. How do you get it right? You have to look at pluses and minuses of this curve. That'll give you pluses and minuses of the derivative function. And from there, you can deduce the increasing decreasing of the original function. It all summarizes into a single diagram like this. Look at the picture. The derivative function hits the x-axis right here, x equal to -3, and right here, x equal to 0, and finally right here, x equal to 3. These three numbers divide the number line into 4 intervals. And then at each of the 4 intervals, I have to consider whether the original function is increasing or decreasing. And then these three numbers are the x-coordinates of the critical point. Now, how do I get the signs of the derivative function? Well, this is a derivative function. So it's above the x-axis here, positive. Below the x-axis here, so negative. Above the x-axis here, so positive. And hit and bounce back, so above the x-axis again, so positive. Plus, minus, plus, plus. Therefore, the original function is increasing when positive derivative, and decreasing when negative derivative, increasing when positive derivative, and finally keeps on increasing because positive derivative. So what do you have? Increasing and decreasing, so we have local maximum there. Decreasing and increasing, so you have local minimum there. And then increasing, pause, and increasing further, so you have neither maximum nor minimum there. This problem did not ask you to sketch the graph, but no, excuse me, let me do it down here. This problem did not ask you to sketch the graph, but it is possible. You can do it like this. Follow the arrows, increasing maximum, decreasing minimum, increasing, pause, and keeps on increasing. Now here I have one critical point, neither maximum nor minimum. Here I have local minimum. Here I have local maximum. At x equal to -3, x equals to 0, x equals to +3 like this. Only the x coordinate. Nobody cares about the y coordinate. And of course you cannot find a y coordinate. Theoretically that's impossible. Why is it impossible is something we're going to discuss a little bit later. Several weeks later, but in any case, just x coordinates only. But then again, we did only half the problem. We have to answer the concavity of the problem as well. That is, find out the intervals at which original function is concave up, concave down, etc. So how do I get that? Well, let's go back up. And let's look at this summary, or maybe this relation. Original function is concave up when the derivative is going up, or the second derivative is positive. Original function is original function is concave down when the derivative function is going down, decreasing, and the second derivative is negative. That's how things are related. It's not difficult to understand. Up is up, down is down. So that's what we're going to do. When does it go up and when does it come down? That is the key. So let's see. Graph is coming down and then going up, coming down and going up, right? Down, up, down, up. So down is down, the up is up. Yeah, okay. So concave down, concave up, concave down, concave up, right? It's easy. Up is up, down is down. Graph comes down, so original is concave down. This graph goes up, so original is concave up. The derivative comes down, so concave down. Derivative goes up, so original is concave up, like that. Here's the answer key, and let me copy and paste this thing. Let's analyze a little bit further. Now look at the original function, decreasing here, coming down. Did I say original? Excuse me. The derivative function is decreasing. The derivative is decreasing, so original function must be concave down, like this. Make sense? Next, derivative function is increasing, it's going up here. Up is up, so this interval is associated to original function being concave up, right here. The derivative is going up, so original function is concave up. Now look at this graph. Derivative function is coming down. Down is down, so original function is concave down. And finally, the derivative function is going up, so original function must be concave up. And as for the threshold, right here at x equals to -1, right here at x equals 1.5, and finally right here at x equals to 3, we have the change of this concavity. Those are the inflection points. So we have inflection points at x equals to -1, x equals to 1.5, and x equals to 3. And intervals of concavity are determined like this. So the original function here is not there. The graph of the original function is not given at all. Still, we can find out the intervals. You can find out the intervals of a concavity through looking at the graphs of the derivative function. What do we look at? Whether the derivative function is going up or down. All right? Do not look at the derivative function is going up or down in part 1 and part 2. In part A and B, don't look at those. If you do, you're going to get automatic 0. Now for part C and D, that's what you're supposed to look at. Let's do this one more time. Okay, let's go to the next problem here. Okay, we have this graph. And then as for part A and part B, we already did the increasing and decreasing nature of the original function. Now let's focus upon the concavity of the original function. This time, let's do it from the scratch. Okay, here's a number line. Doesn't have to be really accurate. Now here I have local minimum at -1.5. Here I have local maximum at 2.5. Are you with me? Here I have local minimum at x equals to 4. And these 3 inflection points divided the number line into 4 pieces. Down below, let's consider the derivative function. And up here, let's consider the original function. Okay. Please note that the derivative function is decreasing here. It's decreasing. That means the original function is concave down. Remember, down is down. Next, here, the derivative function is going up. Going up. So, concave up here in this interval. The original function is concave up. Remember, up is up. Now, the derivative function comes down. Comes down. So, original function is concave down. And finally, the derivative function goes up. That means original function is concave up. Right here. Makes sense? Up is up, down is down. This completes the problem. Oh, actually no, I take it back. Inflection point here. inflection point there. So inflection point at x equal to negative 1.5, 2.5, and 4. And then concave down from negative infinity to negative 1.5, concave up from negative 1.5 to 2.5, concave down to 2.5 to 4, and finally concave up from 4 to positive infinity. You can write all those down if you want to, but as far as I'm concerned, this diagram is perfect. You don't really have to write anything else because I can clearly see everything, including the justification here. Now, if you have all those answers without justification, without this table, then you're going to lose half the credit or more. But with this, you're going to get full credit. Let's see, do we have time for one more? I guess so. Let's attempt. Okay, here's a problem. Again, let's do it from the scratch. As far as the increasing decreasing nature of this problem, the original function is always increasing because the derivative function you're looking at is always positive, so always increasing, but it has horizontal asymptote here to the left-hand side and also to the right-hand side like that. That's a bit different story. Anyway, let's talk about the concavity this time. Okay, we have a number line here. And then down here, let's discuss the properties of the derivative function. Up here, let's discuss the properties of the original function. Now we have local maximum here at -1, local minimum here at 0, and then local maximum here at +1. Okay, I got everything. And then we have increasing, decreasing like that. Do you see that? Now we have 4 intervals to consider. And if you look at the derivative function, it's increasing here, going up. And then again going up there. So concave up here. And then here, going down, and then going down, concave down here, concave down here, and that's it, I guess. Yeah. We have inflection point at x equal to -1, x equal to 0, and x equal to +1. And concavity here, concave up from -infinity to -1, and then -1 to 0, concave down, and from 0 to 1, concave up, and finally 1 to infinity, concave down. We have just a bit of time, so let's discuss the sketch of the original function here again. The original function will look kind of like this, always increasing, yes. And then we have right here at x equal to 0, we have a critical point that is neither maximum nor minimum. But more importantly here, we have horizontal asymptote. Derivative is getting pretty close and closer to 0 again here. So we are looking at horizontal asymptote there. So looking at this kind of graph, increase and then like this. So we have x equal to 0, we have inflection point, and then we have x equals to -1 here, we have an inflection point. We have x equals to +1 here, that's another inflection point. Concave down, concave up, concave down, concave up, concave down like this. And then to the left, we have horizontal asymptote to whatever. And to the right, we have another horizontal asymptote to whatever. And keeps on increasing all the way. That's going to be the sketch of the original function. Well, we have one more problem here, but I'm going to leave that to everybody. Part A, B put together, part B, C, D put together. Okay, that completes section 2.